Light is one of the most enigmatic and fascinating things in the universe. A substance we've struggled to understand for centuries, torn between two poles. Is light a wave or a bunch of particles? Today I want to show you that the truth is actually a bit more complicated.
Hold on tight, because I'm going to take you to a journey through optics, electromagnetism, and the weird world of quantum physics, to the very heart of luminosity. So, without further ado, let's start with Mr. Newton.
After playing around with his prism, Newton had it all figured out. Rays of light were made of particles. Speaking of rays, the idea of light as something that travels in a straight line has been around since the ancient Greeks, but Al-Haytham was the first to realize that rays of light are emitted by bright objects, bounce off the objects around us, and enter our eyes, which is how we can see them. For Newton, these rays were actually particle streams. His theory also made colors easy to explain. Different colors had different particles with different mass. Red supposedly had far greater mass, which was why glass couldn't change its trajectory, whereas with violet, a lighter color, it could.
This view of light went unchallenged for nearly a century because, well, who is going to contradict Newton? But some of his contemporaries, like Huygens, were not entirely convinced.
I'll show you. Imagine a hole whose size we can change at will. We turn off the lights and plug a flashlight into the hole. Question: if I make the hole smaller, what should we see on the other side projected on the wall? If Newton was right and light was a stream of particles, a smaller hole would let fewer particles through, so the projection should be smaller. However, as the hole shrinks, at a certain point, the projection actually starts to get bigger. Trying to explain why this happens with particles is a real problem, but it's simple if we think of light as a wave that's diffracting. It goes through the hole and expands in space. This is one of the many experiments conducted in the 18th and 19th centuries which proved that light behaves like a wave. Here's another classic, Young's double-slit experiment. Shine a light beam through two slits, and instead of two stripes on the screen, you'll observe a bunch of parallel bands. We're seeing waves that reinforce each other in some areas and cancel each other out in others. But waves of what? The medium for a sea wave is salt water. So what's the medium for a light wave? This question was answered by physicists working in the entirely different field of electric and magnetic phenomena. Faraday and co. had a similar problem. Charges and magnetics attracted and repelled each other without even touching, with nothing in between to carry the force. This suggested the necessity of a connective thread, a medium, and that led them to posit the existence of electric and magnetic fields. While trying to figure out which laws of physics governed these fields, they realized the two were connected. If the electric field changed over time, it disturbed the surrounding magnetic field. And if the magnetic field changed over time, it disturbed the surrounding electric field. This mutual influence of electric and magnetic fields gave Maxwell a brilliant idea. If a change in the electric field prompts a change in the magnetic field, then that variation should also trigger a change in the electric field, which in turn should induce a change in the magnetic field. A single disturbance in this electromagnetic tag team would set off a chain reaction, like a wave in the ocean. The real kicker came when he calculated the speed of this disturbance and discovered it was the same as that of light. He found that light was a wave in the electromagnetic field. That was the missing medium. Theory and experimentation high-fived each other, and the wave nature of light seemed like a sure thing. Until physicists got turned upside down.
The discovery of the quantum nature of light is a story with a lot of twists and turns. Here are some videos if you are interested. But the gist of it is that if you lower the intensity of light enough, strange things start to happen. You'd expect a light sensor to continue capturing that wave, no matter how faint. But actually, if your sensor is precise enough, at a certain point it begins to click. Instead of a continuous signal, it registers skips, as if random objects were activating the sensor. This and other evidence bring us back to Newton. It's almost as if light had an atom, an unbreakable constituent, a particle. At first, this particle was called quantum, where quantum physics gets its name, although it was later renamed photon. from the Greek word phos, meaning light. But wait, if those classic experiments proved that light was a wave, how can it be made of particles? Isn't that a contradiction? The answer to this question would have to wait until quantum mechanics took off.
We've talked about quantum rules a lot on this channel, but I'll give you a quick recap. Quantum objects don't necessarily have defined properties. For example, the electrons that form our molecular bonds don't seem to occupy any particular point in space or move at a specific speed. They're indeterminate properties. Well, the same is true of photons and the path they follow. Imagine we have a spotlight and a sensor. Light's quantum nature tells us that a photon will hit the sensor in tons of different ways at once. It can travel in a straight line or take other totally bizarre routes. So why do we see rays of light instead of this tangled mess? It's time for some live quantum calculations. Pay attention, it'll make sense in a minute. Each of these paths has its own arrow, which we call a probability amplitude. The arrow turns as the photons travel along its route, and the direction it's pointing at the end of the journey is the probability amplitude of the trajectory. Question: what's the probability of a photon leaving the spotlight and reaching the sensor? Quantum physics tells us that, step 1, we add up the amplitudes. We string all the arrows together, point to the base, and draw a line from the first arrow to the last. Step 2, we take that length and use it to build a square. The area of that square is the probability we're looking for. This procedure is a bit, It's not easy to understand why we follow these steps, but the important thing is, it works. Look at the ends of the combined arrows and you'll find all the amplitudes of the oddball trajectories. As they're all different, you're basically going in circles if you add them up. The resulting length is going to be very small. It'll only be a fraction of the total length. The ones doing the heavy lifting are the central amplitudes. As they're more or less aligned, they add up quickly, and it's mainly thanks to them that the probability isn't zilch. In other words, they are what allows light to move from one place to another. And what are those trajectories? These. The reason we don't see weird things when we have loads of photons is that the crazy trajectories cancel each other out, destructive interference, while the central paths amplify each other in constructive interference. This is the quantum explanation for why light travels in a straight line. Another example. Imagine we put two solid blocks between the spotlight and the sensor. Now tons of trajectories, and therefore amplitudes, have been omitted from the sum. Only those that can pass through the gap in the middle are allowed. Let's place a second sensor here. What's the probability of it being activated? We trace the trajectories, obtain their amplitudes, put them together, and, well, the arrows are so different that the probability is quite low. If I blast a lot of photons, very few will make it, and I'll get a dark reading. But what happens if I push the blocks closer? Now some of the earlier paths aren't possible, which means I have to remove their arrows from the sum, but with them gone, the circle isn't as closed, meaning the probability is now greater. Now if I blast a stream of photons, the sensor will detect more light than before, simply because the blocks are closer together. This is the quantum explanation for why light diffracts. Last one, I promise, the double slit. Here things are a bit simpler. Light only has two ways to reach the screen, the sensor. Now, depending on what point you choose, the results will be different. In the middle, the two paths are identical, so both amplitudes will be perfectly aligned, and there's a good probability of the photons winding up here. But things change as we move. The arrows aren't aligned anymore, and probability decreases. These are the dark areas in the pattern. But of course, the arrows keep on spinning, and at a certain point they come back around, realigning and increasing probability. This is the quantum explanation for the interference pattern produced by light.
Richard Feynman filled an entire book with these kinds of examples to convince us that light isn't a wave. It's just that the rules behind light, with its cyclical thing, magnitudes that reinforce and cancel each other out, and so on, behave like waves. Light resembles a wave on our scale because we have 10 million photons visually revealing its quantum behavior. But the photons are not what make light ondulate. The real culprit is its quantum nature. Newton would be proud. However, although this made things much clearer, the debate didn't stop there.
The new bone of contention was this innocent experiment. A lamp emits a light beam. An electrical current excites the lamp's atoms to make them give off a steady stream of photons, each marching to a different drummer. The beam is divided into two by a splinter and sent to two different sensors which we can place at whatever distance we choose. We place them randomly, switch on the gadget, and start to see the photons arrive. The result is what you'd expect. Some photons reach one of the sensors and the rest hit the other. However, when the two sensors are at the same distance from the splinter, the skips synchronize. When one photon reaches a sensor, another photon almost always hits the other. They're correlated. And this makes no sense. Photons come from a chaotic light source, where each photon that's emitted bears no resemblance to the previous one. They aren't coordinated at the outset, and yet they arrive at the same time. This is the Hambury-Brown and Twiss effect. Ironically, it's super easy to explain if we think of light as a wave. The lamp emits an electromagnetic wave, the splinter divides it into two equal waves, and the sensors react identically to the wave peaks and troughs.
In fact, Hambury-Brown and Twiss had used this reasoning with radio waves to improve astronomy techniques with great success. But when they applied it to optics, and with few photons, it blew people's minds. Many found it hard to accept. If they haven't been prepped in advance, why do photons tend to arrive at the same time? The answer lay in another quantum facet of light.
One of quantum physics' greatest and latest discoveries was the fact that elementary particles are indistinguishable. Imagine you have two electrons and want to stay on their trail, taking pictures of them as they move through space. The job looks simple enough on paper, you just have to tag them in each photo. The faster you snap the pictures, the less distance the electrons will have moved and the easier it will be to follow them. That way you always know which is which. But the reality is shocking. The electrons don't seem to have a path, they're just constantly hopping around. You may think it's because you're not taking photos fast enough, but you try again and the same thing happens. You've lost the electron's track. Did they cross paths here? Is this electron 1 or 2? You're suffering the effects of their quantum nature. In the interval between each picture, their positions are undefined, and every time you take a shot, you force them to be defined in a certain place. But in that brief time when the electrons are indeterminate, so are their identities. It's not that we have a problem figuring out where electron 1 or 2 is, it's that intrinsically, there is no electron 1 or 2. We know one fact. There are two electrons. But neither has an identity. They don't have a backstory that makes them different. In other words, they are fundamentally indistinguishable.
It's the same for photons. In fact, a photon is a particular type of indistinguishable particle called a boson. This particularity is what produces the Hambury-Brown and Twiss effect.
Think of two photons emitted by the lamp. What is the probability of both photons arriving simultaneously? If we thought it was really hard to tell two photons apart, but hadn't yet realized that they're completely indistinguishable on a super deep quantum level, we take the usual route. Photon 1 only has one way to reach the top sensor, same for photon 2. So we take its amplitudes, calculate the probabilities, and just multiply them. The probability of two things happening at once. Alternatively, photon 2 could go up and photon 1 down, in which case we do a similar calculation. The sum of the two probabilities is the probability of both photons arriving simultaneously. But the problem is that these particles are fundamentally indistinguishable. There is no photon 1 or photon 2. What we have are two photons with two paths to the sensor above and two paths to the one below. You just have to follow the rules. Take the amplitudes of the trajectories between the 2 points, 2 in this case, and add them. And from that sum you get the probability. As you can see, it's 4 times greater than if the particles had been distinguishable. And since it's more probable, that's what we observe in experiments. Once again, constructive interference explains what looks like a wave phenomenon.
Actually, something similar is what makes a laser work. When the laser's excited atoms emit a photon, they do so with exactly the same properties as the rest of the photons swarming nearby. Why? For the same reason they arrived at the same time. Because the amplitudes of those physical situations reinforce each other, making them far more likely than others. The indistinguishable nature of photons is what gives the laser its monochromatic, almost perfect light. Indistinguishable particles that follow the wavy rules of quantum physics. So that's it? Well, just one more thing. Because speaking in terms of waves or particles is too restrictive. We talked about this in the video of the wave-particle duality. We are using words from our everyday reality to describe something that can't be expressed in those terms, something more complex.
And I'm afraid that's the case here. Do you remember the electromagnetic field we left by the wayside? Well, when physicists forced it to follow quantum rules, they saw that the spreading disturbances, we might call them quantum electromagnetic waves, exhibited the same behavior one would expect of photons. The fact that producing them requires an exact amount of energy, that a low-energy photon won't interact with another photon. Here's our missing piece at last. Photons are a consequence of the quantization of the electromagnetic field.
So, what is light? Light is the disturbances that spread across an electromagnetic field, a quantum field. These disturbances have all the advantages of particles, except that they have to obey the quantum rules. When lots of photons come together, this quantum nature is revealed in their wave-like behavior, and all the classic laws of electromagnetism materialize. But while we may have solved the mystery of light's origin, there are still tons of amazing aspects left to explore. Hambury, Brown and Twist's experiment taught us to see light in a new way in terms of its correlations, and introduced us to phenomena people never could have imagined in the classical world. The study of this inherently quantum phenomena is called quantum optics, and it's one of the lines of research being pursued at IFIMAC.
One example of these effects that quantum opticians revel in is photon anti-bunching, which, despite being the opposite of the Hambury, Brown and Twist effect, can be observed in their same experiment. It entails tweaking the photons so they don't want to reach the sensors at the same time. Its demonstration allows humans to observe individual photons for the first time in history, a particularly fascinating sight for fans of quantum communications and computing.
This is just one of many examples of how light behaves in ways that seem impossible from a conventional perspective. To make light behave in these inherently quantum ways, scientists tend to use, firstly, artificial light capturing structures.
These structures, called cavities, range from something as simple as two mirrors facing each other to something as complex as photonic crystals, periodic structures that trap light by interference. Later, the light is forced to interact intensely with matter. Different things can be put inside these cavities, individual atoms trapped using electromagnetic fields, for instance, or quantum dots, tiny semiconductors where electrons are so tightly confined that they act like artificial atoms. This interaction gives rise to exotic new states, mixtures of matter and light. It also makes the light that escapes from the cavity emerge with very strange quantum properties, which can present as unusual coincidence patterns in the Hambury, Brown and Twist experiment.
Researchers have plenty of terrain to explore here, fiddling with properties like the cavity's resonance frequency, the transition energy of atoms, or the intensity and color of the lasers that can be used to excite the entire system. I'll give you an example. IFIMAC scientists theoretically proved that you can actually use these sort of tricks to create a brand new type of light.
A light made of photons grouped in packets. In other words, only emitted in groups of 2 or 3, something they called a photon packer. This new type of light could have interesting applications in the field of multi-photon excitation microscopy. Imagine that you want to observe a live tissue sample. The plan? You inject it with small fluorescent particles that absorb light and later re-emit it on a different frequency. By observing the emitted light, you can reconstruct an image of the tissue. Problem: the photons you need to send to activate the particles are too energetic and might damage the tissue you want to see. Solution: instead of one very energetic photon, send several sluggish ones. That's what multiphoton excitation microscopy does. It illuminates with lower frequency light, in the hope that every now and then several photons will arrive at once and excite the particle together. Less damage and greater tissue penetration. Well, with the Packer, you don't have to wait for this to happen by chance. Photons always travel in groups, allowing us to be far more efficient. Bizarre quantum behavior at the service of biological research.
In summary, light, whether it's a particle or a wave, never ceases to surprise researchers, especially when we take a closer look at its quantum side. That's all for today. We'll be back soon with some more science. And as always, thanks for watching.